Robertson, a programmer and video game designer. I worked in the video game industry for 11 years, but now I'm an indie game developer. So this video, what's it all about? Well, I recently did a self-evaluation and made a list of about 20 different video game algorithms that I understand very well and can implement very easily. I discussed it with my peers who suggested that people might like to learn from me about these various algorithms. So I'm making tutorial videos for each of these video tools in the hope that game programmers and indie video game devs will find them useful. These tutorials do not require that you know C++, but you will have to know how to program and understand game development. These tutorials are not for beginners. They are for coders and devs and will address specific algorithms and techniques. So this video is specifically about particles, more specifically particle systems. What are they? What can they do? Why do I like them so much? This tutorial will discuss my implementation. However, this tutorial will be as much theory as practice. I'm going to show you code, but my implementation isn't very optimal, and we'll discuss why that is. All right. Let's give us a start by actually looking at the app, the demo app in action. Here we have the demo app. You can see I've got 3 little balls bouncing around, some particles coming in from the left side, and a little yellow kind of particle spray in the lower center of the screen. So there's nothing on the screen except 2D particles. There are certainly 3D particles in the world, or in that can exist, and most of the things I have to say about particles will be irrespective of 2D or 3D. Even the technology is essentially the same. The only real key difference between 2D particle code and 3D particle code is which way the triangles face. But in terms of particles, again, I want to talk about more than just code. I want to talk about implementation and use. And as you can see, we've got 3 uses right here. We've got kind of a little fire thing going on here. It's not very good, so let's make it better. And we've got 3 balls bouncing around, and they have red trails behind them. Red trails that could easily be rocket ship exhaust. And then over here we have little green particles that come in from the left edge. And like most particles, they fade away into nothingness. And they have random bits of position and velocity. So I think that the trails of the bullets and also the green snow here coming in from the left are interesting in certain ways that we will get into. But the first thing I want to do is say, well, this is supposed to be a fire, but it's not really fire. It'd be nicer if this were actually something that was, well, something more than fire. So what I'm going to do is I'm going to look around in my code base for a background texture, because that would help us see these particles a little bit better. Go digging through my graphics to see if I have a nice background texture there. I don't really, so let me find one in my code base. We're going to dig around. I know I have a whole bunch of high resolution star maps or star bit maps for the skyboxes of my Artemis game. So why don't we steal one of those real quick and use it as a backdrop on this screen. exe and art, and there's a nice background for you. Yeah, that's very pretty. Let's take that, Control C. Now it's a JPEG file. I wonder if my engine's going to load JPEG or not. I might have to turn it into a bitmap. I mean a PNG file. Those are just formats. But yeah, let's try that. Here we are looking at state tut particles, and here's my code, including some variables we need, and of course this pixie, which is what I call those little balls that are bouncing around. All the pixie has is position and velocity right now. Then I have a function called state tut particle tick, and I'm doing it as a tick because the timing needs to be really nice to get the balls to move in a very smooth way, and incidentally to emit the different particles from the hot part and the cool part. Why do I use the word emit, and why do I have hot part and cool part here? I'll get into that. Those are very important questions though. But here is where we're drawing, and what I'd like to do is first draw. So I'm gonna draw, and this particular bitmap is called Skybox BK. Let's see if that works for me. Map, draw 2D bitmap. I'm going to draw it in the center. Screen width divided by 2. Screen height divided by 2. You're seeing that, right? Yes. No rotation, and I guess scale is 1.0 for now, and that's fine. And the rest of it's good. Let's run the program, compile it and run it, see if that actually gets me a prettier background. Yes it does. Look at that. Now there's issues here, like the fact that I can see the three balls, but I can't see the other particle effects, probably because the background is on too high a level layer. Let's fix that very easily and quickly by adjusting the layer. Normal 2D layer -2. Push that back 2 layers. Particles. There we go. That's I love this. This is good. This is good in a lot of ways. So one of the things I'd like would like you to notice here is that there's an interesting draw difference between the different particles that are appearing on the screen right now. Specifically, the red balls that are flying back and forth seem to be red, and they seem to be as they normally are. However, the green particles coming in from the left and the little yellow particles happening here seem to be surrounded by black smudges. They seem to have black outlines. And of course we didn't see that when we just had a perfectly black outline. But why does this black outline exist? What's going on here with the blackness of these particles? Well, if we get back to the code, you can see that we draw a particle system called hot part and a particle system called cool part. And then you can see here in the particle tick system, we are hot part emitting for the 3 pixies, and then we're cool part emitting for the left edge and for the little yellow, this is yellow, emitter. And so, in the broad brush sense, what we're seeing is the difference between the cool particle system and the hot particle system, which leads me to the first major important lesson that I really wanted this video to be about. And that is that while particles are graphics just like any other, and in the modern age, every graphic thing that goes on the screen is put there by a shader. And so the way we draw is the sky's the limit because it's all completely programmable. However, the great truth is that there's really only 2 kinds of particles, generally speaking, that people use, and that is normal draw and additive draw particles. Now, it's kind of understood that no matter what kind of particle you have, you can see through it or see around it. fading off into nothingness is a very common thing that the little particle images do. Um, so of course that's a common thing. Then of course that's you can break that rule anytime you want. You can make big chunky solid particles, and depending on the presentation you're going for, that can look great too. But uh, it's typical to have particles be transparent or translucent, at least parts of them. Which is again nothing new. A lot of textures do that, and we're talking about textures here. Um, but beyond that, there are two different ways that we normally draw particles, and which is to say a normal way and an additive way. What does that mean? Well, a normal way is essentially no different from anything else you would paint on the screen. You paint a line, you paint a bitmap, you paint some text on the screen. That's the normal way. Essentially there's background pixels and then foreground pixels. And when you paint the background pixels, and then the foreground pixels get painted separately and cover up the background pixels. That's a normal replacement draw, and that's what I'm doing with what I call this cool uh, uh, particle system. Um, but there's certainly another way to draw particles, and the other traditional way to draw particles is additive. What does that mean? That actually means that when you draw on top of something else, one does not cover up. And imagine more specifically one single pixel, and then an additive pixel is placed on top of that. That is not covering up, that is not replacement. It is additive because it literally is adding to the dot. And the astute of you will, of course, know that when it comes to computer screens and computer art, you're really talking about three values of 0 to 255, three byte values. R, G, and B are what you see on any pixel, on any computer, on any screen. The very essence of color on a computer screen is RGB, and more specifically, byte binary byte values, which means from 0 to 255. It's a weird number unless you're thinking in binary or hexadecimal, in which case it's a very round number, but that's neither here nor there. The bottom line is we all know RGB 0 to 255. If you want full red, you go 255 red and 0 green and 0 blue. If you want pure blue, then you go 0 red and 0 green and then 255 blue, and so on. You understand that, and I hope I'm not talking down to you. Well, additive means that if the background color blue value was 100 and the foreground color or the pixel of the particle color was also 100 for blue, then when you add the front to the back, pixel by pixel, then that pixel's blue becomes 200, 100 plus 100. Now if this particle were 200 and this particle in front of it were 100, then that's 200 plus 100 is 300, but color on the computer screen for a single channel like blue only goes up to 255. Well, in that case, additive draw simply means clamping to the maximum value. So if it's 200 plus 100 is 255, because that's the highest it'll go. That's all. What does that get us? Well, we can see for ourselves that it gets us a very hot, bright particle that actually gets brighter as it goes in front of something bright. And if that means that it kind of fades out into white, then so be it. But the bottom line is that the additive drawing method is a very common, very well understood method of how you draw particle images onto the screen. Specifically to get that feeling of hotness, of color and brightness and heat that you would get using a particle system to show off a dragon's breath or a missile trail or a lightning bolt. These are all, you use additive when the thing you're drawing is illuminated, self-illuminated. It's burning, and as you can see from the green stuff coming in from the left side, normal drawing just doesn't cut it. It's there, but it doesn't give that same hotness. So let me give you a bit of an example about this color. Here we have the actual code that produces particles in the wake of the various pixies as they bounce around. And this particular code is specifically a function called emit. So when I was first told how particle systems worked, I was told about the emitter object. You make an emitter object, and then the particles are generated from the emitter object according to the the values carried in the emitter object. At the time, I didn't understand that really that what people were talking about by an emitter object was an object that calls the emit function on the particle system. The point of the emit function is simply to add a particle to the system, fresh new particle. One of the concepts of particle systems is that a single particle system manages a large block of simple particles, and one of the fundamental values of each particle is its lifespan. Over here at the end, I am saying that every single one of the particles that come out of the back of the pixie lives 10 lives. What does 10 mean? Well, in this case, it just means a certain period of time. It could be 100, it could be a 1, whatever. It's whatever number works for me. It's how long the particle lives as it fades out and then disappears. A longer life means it fades out more slowly and then finally disappears later. And as you can see, since I keep looping, I keep generating particles one after another. In fact, this piece of code says basically every 10th time through this function, I get to generate a particle. Probably because, and the reason for that is because this function gets called a lot. Like I believe every 4 milliseconds. So, here's the emit function. The emit function is going to be is about as fundamental as it gets to a particle system. When you write a particle system, when you make a particle system, when you interact with a particle system, you will always be calling emit. Or alternatively, in an object-oriented system, you will always be creating and removing emittors and setting their values. But emittors are just objects that call emit. And what am I doing when I call emit? I'm saying, here's where the particle starts. Here's the direction the particle moves in. Here's how big the particle is. Here's the color of the particle. And here's how long the particle lives. It's a long series of arguments, but that's kind of the point. The particle system handles a bunch of different particles that would do different things and simulate different aspects, like, again, dragon's breath or a rocket exhaust or a torch. And to do that, it needs different arguments. It needs different particles to operate in different ways. I'll get back to that because it's a fascinating theoretical discussion. But for now, what we're going to talk about is, we're going to move on to this and say, I was talking about additive and how it adds color. And one of the ways in which we can see that it adds color is if we take these particles and modify the color. Specifically, all these particles for these pixie trails are always going to have a red component. But in this case, I'm also going to change the component of green and blue. I'm going to change them randomly all over the place. Now, I just got through telling you that in the traditional world, colors go from 0 to 255. In this particular implementation, colors go from 0 to 1. Floating point. It's a thing. You learn to translate between them. Sometimes it's easier to go 0 to 255 because you're close to the metal. Sometimes it's easier to go 0 to 1 floating point because it's just easier to do math that way. But in any case, in this case, it's all 0 to 1. So I'm basically saying you're getting a random color, RGB, except it's always full red. Now the cool thing here is that what that's going to do is that's still going to make it primarily red, but it's also going to make it very white because, as you know, in the additive way that pixels are painted on the computer screen, white is full red, full blue, and full green. On top of that, remember, we got a bunch of particles that are all additive that are going to stack up on top of one another, which means that their images or their colors are all adding to each other. And that means that as long as there's color greater than 0 in each of their 3 channels, you stack enough of them up, you're going to get white. So what this is hopefully going to give us is a much more hot, much more reddish, but also whitish particle effect, just by changing this color to be more random. Let's see if that's true. I'm going to run the code now, and let's see how that changes the pixies. Alright, so immediately what we see is that there's a lot more random colors in the pixie colors. And that's not really what I was going for. I was going for more complex hotness. One of the reasons we see more random color is, of course, because we got the blue in there, which is not necessarily a normal color for torched style fire. And also the particles really aren't stacked up as much as I said they were. They're stacked up a little bit, but they're not. So let me do a couple things here. First off, I'm going to back this off so that there is no blue color except for a teeny bit. So there's just a little bit of blue in every particle. And the second thing is that I'm going to change this so that there are 5 times more particles. 0, yeah. That should work. I think it works. Is it not working? Oh, no. I need a double equal, or it won't compile. So more particles, less blue. Let's see what we get. That's what I was looking for. So with less blue and more particles, you can see how the particles not only overlap each other, but they essentially intensify each other by the natural behavior of the additive drawing method for the particles. And now you can see how additive drawing makes a particle system really hot, really pop out, really look burning like fire. And that's cool. And you can also see that there's kind of chunkiness in the flame trail, and that chunkiness is entirely due to the random number of the green value. So we can make it even a little hotter by changing the blue value to 3. That's going to get us closer to white quicker. And another way that we can make things a little bit hotter is we could actually modify the fire trail. So this code right here is the movement over time of the particle, and we got it set to 0. Let's play with that. Let's actually change it so that it actually spreads out. Now this is kind of a little bit ugly because it's going to spread out in a boxy kind of way, but that's okay for now, for this, and it's not spreading out much. It's probably going to spread out too much, but we'll see. Okay, so yeah, now you can see the particles are spraying out very quickly in all random directions, which, there's a place for it, but it's not here. One of the distinctive things about this is that we had a cool fire trail where individual particles were hard to see. And then we messed it up by having a lot more movement in the individual particles, and now it's so much easier to see the particles in this fire trail. Now, it's a philosophical discussion, or more specifically an aesthetic discussion about this, because I have certainly heard people say that if the player can see the individual particles, then you're doing it wrong. In other words, the idea is that you use a lot of particles, a lot of very simple particles that are drawn very quickly and easily in order to achieve a graphical effect that is much greater than the sum of the spray of particles you put on the screen. And I think there are a lot of counter examples of that, a lot of different uses of particles where the individual particles are very clearly obvious, and yet people still think, hey, that's a pretty good explosion, or that's a pretty good fire, that's a pretty good use of particles. So I think it's a kind of an aesthetic choice, but I think this really is a great illustration of that. We had something that was a very cohesive flame trail, and we screwed it up just by adding too much randomness to the particles, and now it's specifically random in the sense that the individual little particles are much more obvious. So let's go back and modify the numbers here. Float move equals 0.1. And let's change it so that the particles don't go all over the place. They just go a little bit. They go 1/10 as much as they used to. All right. Now this is what I want. We still have a cohesive flame trail, and you don't really notice individual particles so much. But because the individual particles are going off in slightly different directions, you get a lot more fuzzy trail. You get a lot more interesting texture in the trail. It's more interestingly distinctive. I like that. That's good. And what we've just been going through is a perfect example of why I'm such a fan of particle systems in my video games in general. That kind of fiddly twiddling to get just the right effect is totally fun for me as a programmer. I love it. I could spend hours doing that kind of thing. It's very enjoyable to play with particle systems until they look right. And this gets me to another point that I wanted to talk about in this video, which is simply that one of the greatest things about particle systems, once you actually have your own particle system technology ready to go, is that good enough is easy and fast. You may not be able to quickly get perfection, but you're guaranteed to very quickly get something good. Something, hey, it took only like 5 minutes to throw in, these flame trails for these things, and they look great. And we only had to fiddle with it for 5 or 10 minutes. That's kind of how particle systems generally are in my experience. That they're about how to get something fun and easy on the screen quickly that looks pretty good. And you know that if pretty good is not good enough and you really want something great, you can get it. You just have to work longer at fiddling it and getting it to be exactly what you want. So, let me look through this list. One of the things that I certainly want to reiterate about particle systems theoretically is this idea that you use particle systems in a lot of different ways for a lot of different general purposes. Again, your dragon's breath, your missile flame trail, your torch on the wall, your snow, your rain, your dust kicked up, your sandstorm, anything that's lots of little particles that individually are fairly simple. And even that is something we need to talk about as far as philosophical programming choices. But because of that, you and I make lots of different kinds of games. Not every game has a flame trail. Not every game has a dragon to have breath in. And this is essentially an important part or point about particle systems in general, which is that they are not one size fits all. They are dependent on the game. Whatever game you're making, however you want to use the particles, it's going to be slightly different or a lot different depending on the game you're making. And that means that the idea that you can have one single particle system, one piece of monolithic code called the particle master that does every particle for you, is essentially the poor way to look at it. It's not the right way to look at it. It's not the correct way to look at it. And part of the reason for that is that there's kind of one of the beauties I thought when I learned about particle systems and how they worked and how they were supposed to work is the idea that you can build a particle system and it doesn't have to be good, and it doesn't have to be efficient, and it doesn't have to work well. Because the point is that you're kind of expected to iterate on that particle system. You're expected to keep making it better. And one of the simplest impetuses for making it better is that you have a particle system and it works, but it doesn't work well enough for your application. You have a flame trail, but you're just not getting it perfectly the way you want it to. Well, you need to build a better particle system, and most people don't throw it away and start from scratch. So they'll go ahead and modify the existing particle system, and by modify I often mean um, optimize. Now, optimize has a particular meaning here, or at least it's important to think about it, because the point of a particle system is definitely to draw lots and lots and lots of little particles quickly. And again, since there's a kind of a thought that if you draw two particles, well, that just doesn't look that good. But if you were to draw 100 particles in a specific way, then those 100 particles together come to make an effect that is better than the sum of all particles. That's what you're looking for. Which means that more than likely, when you're doing particles, you're always thinking, I wonder what could be done. I wonder how much prettier my game could be if I, say, doubled the number of particles that my system could handle. Well, you can't double the number of particles that your system can handle without a slowdown unless you optimize. And remember, I was just saying a second ago that one size fits all doesn't really cut it in the world of particle systems. It can, and lots of people use a simple off the shelf part, but the truth is, if you want the maximum out of your particles, you have to optimize for what it is you need particles to do for you. And again, that optimization comes into issues of speed. How many particles can you draw per frame before there's a significant slowdown? Um, Anybody who's ever done particles on any game that has ever shipped has thought about the issue of, is my particle system using up too much speed? Can we do these particles faster? Can we do more particles without sacrificing speed? It's a very common understanding of particles and particle systems and what they do. Um, so this is why I'm saying that particles systems are not one size fits all, even though somebody might tell you different. And also, particle systems kind of exist to be continually optimized. Now, this flies in the face, interestingly enough, of an old saying by an old wise computer programmer who said that optimization, or sorry, what he said was premature optimization is the root of all evil. He was talking about it in kind of specific compiler terms, but I love the statement. I love the quote because it echoes it means so much to me personally. I have actually in my career and in my personal coding have been bitten many times by the idea that I chose to optimize too soon. That premature optimization is indeed a bad evil. Is it the root of all evil? Maybe in the terms again of a compiler, but it certainly is. Premature optimization is certainly a big bugaboo with me, um, and uh, and since optimization is kind of a part of life when it comes to particles, it's something to think about. So, if we're going to look at the particle system code that I have in a second, and you'll see that it's not particularly well optimized. But that's the point, is good enough often works great for a particle system. And if it doesn't, well, you know where to go. You know it's time to optimize, you know it's time to revisit the code, make it better, faster, stronger, more applicable. So, I've shown you hot particle emit, and of course down here cool particle emit. Cool particle and hot particle are just particle 2D manager objects that I created at the beginning of the program here. Each of these particle managers has 1,000 particles inside it, and each one uses the bitmap smoke 1. So what is a 2D particle manager? Let's actually look at my implementation of my 2D particle. And it's, again, not the greatest in the world, but it works. So I have a structure which is just the particle itself. And notice that life always starts at 0, and there's a life left and a lifespan. So this is its age, and this is its age in which it dies. Then, of course, I have position and delta position. And even though we haven't been using it in the graphics, here I am with a gravity pulling down on the screen or up on the screen, depending on the sign of the calculation. A scale value, and that's per pixel. Color and Kerr color. Again, um, the idea of the particle is that, in at least these particle code, is that the particle always fades out over its entire lifespan. So life left is modified, is used as a coefficient to the Kerr color. So here I am with the particle manager. Here's the actual object of it. Here's the arguments to creating a particle manager. And then I have my tick. That's where things move, of course. My draw and my emit. And I have a helper function called clear all particles, just in case I erase or stop the app, go do something else, and then come back. I sometimes want to erase all existing particles to start fresh, so that weird particles don't show up in weird places. This is a reference to the bitmap, and also for the draw process, which is another word for the shader. And then here's the actual array of particles and how big it is and my place within it. So if we look at the particle object here, here's the constructor. I'm firing up I'm grabbing the map in the process, whether it's normal or additive, and setting up the array. Now, why am I using an array here instead of a map or a standard vector? Well, for simplicity's and speed's sake. I mean, this is, particles are about handling lots and lots of particles quickly, so speed is something you think about. Not that I'm doing a great job at it, but, I did think about it. I did, honest. Okay, so this tick loop goes through every single one of the particles, and if it's alive, it modifies it. It says, well, it has less life than it did, and its color is its color divided by its lifespan, or coefficient of how much life is left, so the whole thing fades. And then also here's the gravity code for the DX and also the movement code. So it's very simple, iterative through the entire array, and of course skip it if the particle is not currently visible on the screen. And then here's draw. It's the simple thing, and it's the same exact thing. Loop through the whole thing. If there's a life, then do the draw bitmap of the actual image. And then here's emit. Remember, emit is the function that you call when you want to add a particle to the screen. So call it once every time the rocket flies across the screen so that a particle of fire comes out the back. If there's a bomb or an explosion or a fireworks explosion that you want to put on the screen, then you want to make a loop, 100 times. Call emit 100 times in a row to make a big spray happen all at once. And that takes the various arguments, and then this code basically just says find the next dead particle. This code says if I can't find a dead particle, skip it. I'm saturated. I'm using all 1,000 particles. I don't have any more room for a new one, so I don't accept your emission, your emitting order. And then I just set that particle to fill in the blanks. And this little tool just kills all the particles. So as you can see, it's not actually very hard. This particle manager is not complicated. It's also not terribly efficient as particles could be and should be. But it's also not terribly complex. So let me take a little side thing here and talk about my time at Acclaim Entertainment in 2000. I went to work at Acclaim, and I was on the team that did All-Star Baseball 2002 and 2003, starting with the PlayStation 2 and also the GameCube for 2003. Um, and I was in charge of the particle system there, mostly because I raised my hand and said, "Oh, can I do particles? Particles are fun." And they said, "Sure, Tom, why not?" And so I did, and I did the rain and the snow and uh, the dust kicked up by the players as they ran through the bases, and if they were running in rain, then the water splashed up by the characters. And also for a cold day, I did their breath, which was made up of puffy cloud particles. Um, those were the particles I did for that game, and I had actually a lot of fun doing it and a lot of fun tweaking it. Just as you saw me tweak the fire particles that we were just doing, I did a lot of that for the various pieces of the baseball game until I thought I had something that I thought was really good. Um, anyways, I enjoyed making it, and um, and of course, I had to go through the same system of optimizing particles over the time. And somebody saying, "Well, Tom, I don't think we can use the particles on these fields because they're so complex graphically that there's no room left or time left to use the particle system. It would slow the game down." And so I was forced to go, "Well, I'll have to optimize my particle system, won't I?" Um, so if you're a programmer who just loves programming, this is one of the ways in which I think particles are great, because the whole system cries out for optimization. Um, However, the more particles you make and the more particles you want to make, the more complex particles are. Notice that I have things like where the particle is and where it moves and what color it is and how big it is and how long its life is. But that's not nearly as many different complex things as a particle system could be. A particle system could be a great deal more particly or a great deal more complex than that. Particles could expand over time. Particles could slow down or speed up over time. Particles could change color in complex ways, throughout their lifespan. Um, all these things are things that particles could do, and if you use them right, they could result in really interesting effects, like the waves or the wake of a boat across water, or the duality of smoke coming off of a fire full of wet wood, um, or a mist in the air, or a nebula. These are all things that you could theoretically do with your particle system, and you might want to add features, add complexity to your particle system. Um, but adding complexity, adding smarts to the individual particle, making the individual particle less stupid, is against the rule of making the particle system more optimized. So you can see the natural tension and the complexity there, which again, from a programmer's point of view, is actually fun to wrestle with. Um, and so it almost is a philosophical debate, and I've always come down on the side of making very simple particles, but making a lot of them so that you can create something out of a bunch of particles that looks more than just a collection of particles, but turns into something distinct and interesting. Whereas I have worked with and also seen the work of other people who have philosophically the exact opposite point of view. And let me more specifically talk about, again, Acclaim, because there were some coders who had a lot of code left over. They had left Acclaim by the time I showed up, but they had a long reach in terms of the technology of the company. And when I went through and looked at their code, I couldn't believe how complicated their particle systems were. I looked at it and said, I wouldn't even call this a particle system. Their particles were able to do collision detection, complex collision detection against a 3D environment. They could stick to walls, they could bounce off walls, they could stick to each other. One particle could spawn another particle. The sky was the limit. There were some crazy complex things that their particle systems were doing. And I scratched my head and go, why would you do this? Because you're making all your particles slow. You're making them so smart. How can you even call them particles anymore? That's, the point of a particle system is to be efficient and simple. Yeah! So, It broke my brain, but that's okay. Other people shrugged and said, "Get over it, Tom." So I guess I did. Maybe. Except I'm talking about it now, so I wonder. Be that as it may. So that's one of the things I found at Acclaim in my experience at when I was at Acclaim, actually implementing particle systems for an actual saleable product. I had a lot of fun. But it goes to show that there's a lot of philosophical depth to how you handle particles and why you make particles, what you use them for, how you make the particle managers, the particle systems. Um, Again, not one size fits all. It should fit you and your needs. Um, and I'm not sure if I was made it particularly clear, but I firmly believe that one of the most pretty things about a particle system is the way that you could put a bunch of particles together and suddenly you have an effect that isn't really even particles anymore. It's something more than the sum of the particles, like these fire trails behind. The average player is not going to look at it and go, "Ooh, those particles are, I see individual particles." They're not going to do that. They're going to see the cool fire trail, and that's all they're going to see. And if it's made out of simple particles and used a lot of particles, that's okay. That's what the particle system was for. So, um, I think I've talked about particles as much as I would like to talk about particles in theory. And I think we've looked over the code. We've certainly looked over my particular particle manager object that I wrote here and seen how fairly straightforward and simple it is. Okay, one thing I did not discuss, but I need to discuss before we go, is the fact that in this modern age, when somebody says, "Hey, we need to optimize the particles," then the response is pretty much universally, "Okay, well, we need to do more particle stuff on the GPU." And that is not only quite true, but that is absolutely the way the professionals do it. Obviously, my particle system, no, no, this is the only part of it that actually gets anywhere near the GPU, and I'm just doing normal two-dimensional drawing stuff here. If I wanted particles to be really, really fast, so that I could make millions of them on screen, I would try to take as much of my particle 2D manager object as every line of code I could and turn it into a shader, piece of code that runs on the GPU. Because the shaders of the and the GPU is very parallelized, and therefore it's pretty much guaranteed to be incredibly efficient compared to your GPU particle solution. Um, and the only reason I haven't done that yet is reference earlier when I said premature optimization root of all evil, and I also said that I don't believe you can or should try to have a one size fits all particle system. But having said that, it sure would be nice one of these days to make a GPU particle system, because I know that it would be essentially 100 or 1,000 times faster than the particle system I have now. And if I need that speed, I know where to go: straight to the GPU. And people have been doing that forever. I mean, I watched a video of a developer who was part of the Jack and Daxter project on the PlayStation 2, and he told that video he said how they had essentially moved 99% of the particle system onto the GPU. Of course, the GPU on the PlayStation 2 is a specialty, wonky case, kind of wacky, oh my gosh thing, which is not within the realm of this video, but well worth looking up if you're interested in that kind of thing. But the bottom line is, particles on the GPU are where it's at, except if you don't really need that, and then don't try to make something that's one size fits all and is optimized before it really needs to be optimized. Okay, so let's look one more time at the actual code I'm running. You can see that I'm just calling draw on my two particle systems. Here's in the exit function, of course, I delete the two particle systems. In the entry function, I create the two particle systems. In the timed tick function, I call down here to this function, and that emits and emits. Now, notice one thing is that it seems that I'm emitting in the tick function and drawing in the draw function. And that's quite true, and that's perfectly fine. If you want to, though, there's nothing that says you cannot call the emit function inside of your draw function. Not the cool parts, not the particles draw, but the game's draw. You could easily put a hot part slash emit here, and it would work just fine. You might have speed problems over fast computers versus slow computers, and that's why I'm doing it in the timed tick to make sure that my speed is the same no matter what computer I'm running on. But but the bottom line is that the emit just makes a new particle and adds it to the list, and then there's draw, and then there's also tick. Don't forget to tick your particle systems, or they'll never die or move. Okay, that's particles. I'm glad that you were here, and I hope you learned something. I hope this was useful. And I'm going to make more videos like this. So if you like what you see, go ahead and press the subscribe or the bell button, and so that you can be notified when I make another video. I really appreciate you being here. Thanks, and I'll see you again.